Alright, hello class. Today we're going to be talking about section 3.6, which is on the chain rule. Now the chain rule is easily the most important rule we'll learn, but it's also the rule that students tend to have the most trouble with of all the rules. What the chain rule basically does is it's an extension of all the rules we've talked about to more general places. Right, so this is basically just an extension of derivative rules. Right. So here's the question. Right, we have the power rule, we have the exponential rule, we have the sine, cosine, all the trig function rules. Right, so say we know that the derivative with respect to x of x to the 10th is 10x to the 9th, right? That's our power rule. And we have our exponential rule, which says that the derivative with respect to x of e to the, let's just say e to the x. Let's make it simple to start with. E to the x is itself e to the x, so there's the exponential rule. The question becomes, do these rules apply if I have something more complicated in this function instead of x, right? So do these rules apply beyond just x? Right? So in other words, can I apply the power rule to something other than just x to a power? Say x squared plus 3x plus 1 to the 10th. Right? Does it work for this thing? Because this isn't x to the 10 anymore, it's some stuff to the 10th power. But does the power rule still apply? Or for example, maybe instead it's the derivative with respect to x of e to the x squared plus 3x plus 1. Right? So instead of x, say just e to the x, now we're looking at e to something else, e to the x squared plus 3x plus 1 in the exponent. Okay. So that's the question. Do these rules that we know, the power rule, exponential rule, all the trig rules, do they work beyond just x's? Can we expand all these rules we have to more complicated functions of x? And the answer, right, is yes, we can. Okay, but it's a little complicated. Okay, but with a cost. All right, so there's a cost to doing this. And what does that cost? Well, we'll talk about that in a second. But first, let's actually just define the chain rule in terms of how the book or a mathematician would tell you what the chain rule is. And then I'll talk to you about really what it means for you. Okay, so let's start with, say, a way to define the chain rule. And we'll look at two different ways of doing this using both function notation and the Leibniz notation. Okay, so here's what the chain rule basically says. All right, if z is a function of y, so let's say z is an expression of y. In other words, it's z of y. Or say z, as an example, say z is equal to y squared plus 2y. Right, that would make it a function of y. And if y, on the other hand, is a function of x, right? So y of x, right? We could write y as y of x, or y is equal to x cubed minus 1. Then the derivative dz over dx, so the derivative of z, our expression z with respect to x, is going to be dz over dy, so the derivative of z with respect to y, times the derivative of y with respect to x. Okay, so So as we can see, this isn't really a proof or anything, but just from this expression here, if you were to use fraction arithmetic, right, these dy's would actually cancel and you'd end up with dz over dx. Now the important part about this is what's happening is if we have this expression in terms of y, so we're taking the derivative of just z with respect to its input y, and then we're multiplying it by the derivative of y with respect to its input, which is x, and we're just multiplying the two. Another way to think about this is if you have a composition z of y of x, if you take the derivative of that, z of y of x, it's going to equal to z prime of y of x, okay, times y prime of x. Okay, so what this is essentially saying is this is the derivative of the outside function with the inside function left alone. Okay, times the derivative of that inside function. Okay, so this may not make a whole lot of sense in this term, but essentially what this is, if you have you start with the composition f of g of x, this is how we're used to seeing it, right? And we go to take the derivative, it's going to be the derivative of the outside. Okay, so f prime of x, okay, times the inside left alone, okay, times the derivative of the outside. Right, this is what the chain rule says, that when you take the derivative of a composition or a more complicated type function, it's going to be the derivative of the outside with the inside left alone times the derivative of the inside. So if we go back to our question from before, okay, our question from before was, do these rules apply just beyond just x, right, these two rules? And the answer was yes, right? If we go back to what our answer was, yes, but with a cost. The cost is that you must multiply by the derivative of the inside function. Okay, but other than that, these rules actually do extend. You can generalize them, you can extend them just fine. So, for example, let's look at this example we started with, or we started our question with, right? The derivative with respect to x of x squared plus 3x plus 1 raised to the 10th. Okay, so what I'm going to do is I'm going to actually utilize some of this notation I looked at to begin with the z and the y. We're not going to do this a lot. I just want to show what's going on. So what I'm going to do is I'm going to say that over to the side here, what I'm going to do is say that z is equal to y to the 10th. Now why is that? Well, that's my outside function, right? If I cover up this inside function, I'm just taking whatever's there and raising it to the 10th. So I'm going to call that on the inside y. And what is that on the inside? Well, I'm going to call y x squared plus 3x plus 1. Right? And so that means that x, or z, which is y to the 10th, is actually going to be x squared plus 3x plus 1 to the 10th, because I take that y and raise it to the 10th. Okay? So from here, right, what I'm doing is basically taking the derivative of respect to x of z, right? So this is actually dz over dx, what we're taking here. And according to the chain rule, right, this is equal to, so let's find what the chain rule said. Dz over dx is going to be dz by dy times dy over dx. Okay, so let's look at this. The dz over dy. Well, here's z in terms of y, right? It's y to the 10th. So what would the derivative of z be with respect to y? Well, think about it for a second. Y to the 10th, the derivative of y to the 10th, if we're taking the derivative with respect to y, is 10 y to the 9th. Okay. All right, then I'm going to multiply by dy over dx. So y, in terms of x, is x squared plus 3x plus 1. And so the derivative of this thing, dy over dx, right, I can actually do it up here. Let's say dy over dx is 2x plus 3. Okay, so I'm going to move that down here. So this whole thing is times 2x plus 3. Okay, and the last thing I'm going to do is plug this y back in to this y. All right, I know that y is x squared plus 3x plus 1, so I'll rewrite this as 10 times x squared plus 3x plus 1 raised to the 9th, then times 2x plus 3. Okay. Okay, so that's actually the answer. That's the derivative. But the problem here is using this. It's you know, kind of long-winded, right? It's kind of complicated. It doesn't really make much sense. Hopefully it does, but we don't want to do this every time. What you can realize instead is that what we'll do is just use the power rule, but multiply by the derivative of the inside. So I should say, instead of writing it like this, is that you apply the power rule to the outside function, and then multiply by the derivative of the inside function. Okay, so for example, if we just do the same example again, right? I have the derivative of, I want to take the derivative of x squared plus 3x plus 1 raised to the 10th. Well, I have this stuff in here raised to the 10th, so I'm going to ignore that for a second. If it was just x to the 10th, the derivative would be 10. I move it down, this stuff to the 9th. So this will be 10. This stuff to the 9th. That's what I'm doing. Right, so let me just write this stuff in, left alone. So that first step, you always leave the inside function alone. Then you're going to multiply by the derivative of the inside. And so the derivative was, or excuse me, the inside is x squared plus 3x plus 1. So now I'm going to multiply. Whoops, it'll be 2x plus 3. Okay. So here is the derivative of the inside. And here's the derivative of the outside with the inside left alone. Here's the derivative of the outside. Notice I use y here just to be careful. Okay? So, what this really tells us is that we can extend our derivative rules all we want, provided we multiply by the derivative of the inside. Okay, so here's that written out some. Right, we can extend all our rules by multiplying by the inside. So for example, if I decide to take the derivative with respect to x of y to the p, so instead of just x to a power, now it's a function of x to a power, like y to a power. What I'm going to end up getting is p times y to the p minus 1 times the derivative of the inside, which is what this little thing is here, the dy over dx. Then it's a little scrunched up, but now the derivative with respect to x of e to the y, okay, is itself e to the y, but now I just need to make sure that I multiply by the derivative dy over dx. Okay, so the derivative of the inside function y. Okay, derivative of sine is cosine, but if I have sine of y, something that's not x, so notice this, I'm trying to take the derivative of sine y with respect to x. It's going to be cosine of y, the inside's left alone, times the derivative of y. Okay, and the derivative of cosine y, I'm taking it with respect to x, will be negative sine y dy over dx. And you see the pattern continuing. Just got messed up a little bit. From here, that all of our derivative rules stay the same, pretty much, except that you must multiply by the derivative of the inside. Okay, another way to think about this that I find helpful is if you want to extend your power rule to say the derivative with respect to x of the stuff, just a bunch of stuff to power, it's going to be the power times the stuff left alone raised to the power minus 1. Then we just have to make sure we multiply by the derivative of the stuff, right? Or the derivative of the inside. Another example, if you had e to the stuff, the derivative will be itself e to the stuff times the derivative of the stuff. Okay, so back to one of our earlier examples, say that one of the first questions we started with, if I wanted to find the derivative of e to the x squared plus 3x plus 1, right? It's all about identifying this stuff, that inner function and that outer function, right? So that inner function is x squared plus 3x plus 1. The outer function is e. So this is e to the stuff case. So its derivative will be itself, so e to the inside function left alone, times the derivative of the stuff, which will be 2x plus 3. Okay, so what we usually do is we tend to, on most of these, actually write the derivative of the stuff on the outside, but it really doesn't matter. But typically with e's and sines and stuff, this thing looks better. Okay, so let's look at some examples, but basically here's my e to the stuff piece, and here's my derivative of the stuff. So let's take a look at some more examples. Okay, so let's start with an example, a simple one, right? We're just going to do y is equal to x squared plus 1 all squared. So the nice thing about this example is going to be we can actually check it not using the chain rule, right? Because originally what we would have done with this problem is just FOILed this out, right? We would have just said, hey, FOILing this out, this will be x to the 4th plus 2x squared plus 1. Then from here we would have found that the derivative with respect to x is going to be 4x cubed plus 4x when it's all said and done. So we don't actually need the chain rule on this one, but it actually makes it a bit faster. I think we don't have to FOIL out, but let's see. If I take the derivative just using the chain rule, so first I have stuff squared, right? So this is a stuff squared case. So the derivative is going to be 2 times the stuff to the 1 times the derivative of this stuff. Right? So what I'll end up with is 2 times the stuff on the inside left alone, raised to the 1, okay? Then times the derivative of the stuff, which will be 2x. Okay? And there we go. So here is the derivative of the stuff. Let me write that out in red. Derivative of the stuff here. And here's the stuff left alone, and it's being multiplied by 2 and being raised to the 1. So we're just applying the power rule, but to something a little more complicated. All right? So if we simplified this out, say I distributed this 2 across, I get 2x squared plus 2, okay, times 2x, and when you multiply that all the way out, you get 4x cubed plus 4x. So we actually got the same thing as we would expanding and then using the power rule. In fact, that's going to be true throughout. No matter what rule you use, as long as you're using them all correctly, you're going to end up getting the same answer as someone else who maybe uses different rules. So here, if you expand and then take the derivative, or if you just go straight to the chain rule, you should get the same answer, okay, provided you did all your steps correctly. Now, am I ever, say on a test, on your worksheets I might specify, but on a test am I going to specify what rule you're going to have to use? No. Okay. And you might be asking, well, you know, a question I get a lot is, when do I use the chain rule? And the answer is actually always. Okay, you always use the chain rule. The thing is, you may not have realized it, but when you're actually taking derivatives of just x to the power, like x squared, right, you get 2x to the 1, and then what would be the derivative of the inside here? Right, what's the derivative of just x? Well, 1. So we are actually always multiplying by the derivative of the inside. We're always using the chain rule, we just didn't realize it until now. Okay, so we're technically always using the chain rule. Now you might be also thinking, well, I won't use the chain rule because like this one, I could just expand this thing out, and that's a lot easier. And it's true, but you know, if you had something like this, y equals I don't know, like 3x to the 5th plus 6x squared plus 33 raised to the 100th. And I asked you to take the derivative. Well, if you didn't have the chain rule, this would be a beast, right? Expanding this thing out, right, raised to the 100. Imagine doing that. Just think about how long that would take to expand that out and then use the power rule on every separate piece. This is potentially a 500-term polynomial when you multiply it all out. Okay, potentially. I don't think it would be, but it'd be close. All right, and it's already way too long. So, but with the chain rule, all I do is I say, hey, I have some stuff on the inside here. Right, I often just cover it up. I have stuff raised to the 100th, so the derivative will be 100 times the stuff, and often I just leave the thing blank and put 99. Then I copy this part down, just verbatim. Right, so I get 100 times 3x to the 5th plus 6x squared plus 33 raised to the 99th, and then we have a cost. The cost is we just multiply by the derivative of the inside. So the derivative of the inside would be 15x to the 4th plus 12x. And we're done. So this derivative is so much faster, so much easier to do, so much easier to complete when we have the chain rule. Could we have done this problem without it? Yes, but we'd be here all day trying to figure it out, right? And we'd probably make a mistake somewhere and get a wrong answer, whereas here, it's just a single step and you're done like that. Okay, it's no problem. All right, so let's look at some more examples. Okay, let's say we had y is equal to e to the 1 minus square root of x. All right, so to do this one, remember you may need to simplify this. Some people don't. Right, some people can actually just see it in their head, but whoops, I didn't actually do anything. If you need to simplify this, go ahead and make that a step all to itself, right? 1 minus x to the 1/2, and then we can actually apply the chain rule, right? So the chain rule is going to be, so we have e to the stuff, so that's the e to the stuff case. So remember that's going to be itself times the derivative of the stuff. So this will be itself, so e to the 1 minus x to the 1/2. Okay. Now I'm going to multiply it by the derivative of the stuff. So the derivative of the stuff now is 1 minus x to the 1/2. So the 1 will disappear, and now I'll get minus 1/2 x to the negative 1/2. Once we finish this off. And for me, that's good enough. You can check this off and keep going. But some people prefer you to simplify. And what you could do is say that this is negative e to the 1 minus square root of x all over 2 square root of x. And if you were so inclined, but again, I think for now, the test is good enough for me, but if you're playing with your online homework, it's probably going to want something like this. Okay, next example, let's say we have f of x is equal to sine squared x plus cosine x e to the negative x. And you know what, to make this a little more complicated, why don't we make this sine 8. Now, for those of you, sorry about that. For those of you who don't play with trig functions enough, sine squared or sine 8th x is the same thing as saying sine of x all to the 8th. So this is technically a power rule situation because we have stuff to the 8th. Okay. And then I'm going to leave this piece alone. So sometimes when you simplify, you actually will simplify one piece and then not mess with the other piece. But you still need to take a whole step to simplify. And this, as we can see, is cosine of stuff. Okay. So here, all right, so this step now is going to be the derivative. Make sure you mark that as well. I see a lot of people who don't. But something to the 8th. So the derivative of that is going to be 8 times that something to the 9th. Right, so we just plug that in verbatim. Oh, sorry, I went the wrong way. Oh. To the 7th. So 8 sine of x to the 7th. Now, times the derivative of the inside. And the derivative of the inside is going to be cosine of x. Okay? Now, I have cosine of some stuff here. Right, cosine of stuff. So what's the derivative of cosine? Well, it's negative sine. So instead of this plus sign, I'll go ahead and change that to a minus. This will be a minus sine of e to the x minus e to the negative x. And now I'm going to multiply by the derivative of the inside. And the inside, right, this is my inside. So the derivative of the stuff here, well, the derivative of e to the x is itself, and the derivative of negative e to the negative x, well, the derivative of e to the negative x is, I'll just write it, negative e to the negative x. Okay, so here's the derivative of the inside, and this one I would simplify. I would make sure I'd write this a little cleaner, so that this is actually 8 sine to the 7th x times cosine of x. minus sine of e to the x minus e to the negative x, right, multiplied by e to the x plus e to the negative x. Okay, and that is that, as they say. And yes, so go ahead and leave it like that. Okay, next example, let's say we have y is equal to tangent of 3e to the x over 2. All right, so for this one, this is a tangent of stuff. So what is the derivative of tangent? Go ahead and spit that out for me, or tell me, or whatever while I'm talking. Derivative of tangent of stuff is secant squared of that stuff. So a lot of people mess this one up and they'll say secant squared of x and then this, but it's just secant squared of that stuff, right? So you just copy this in verbatim. Okay. Then we multiply by the derivative of the stuff, and the derivative of 3e to the x over 2. Well, this derivative of e to the x over 2 is 1/2 e to the x over 2, so this is going to be 3/2 e to the x over 2. Okay, so here is my stuff left alone, and here's the derivative of the stuff. Okay, and from there we're done. We could rewrite this a little bit so it looks a little better. I mean, often what people will do instead is the constant term goes first, then probably your e, right, and then your secant squared 3e to the x over 2. And there you go. Okay, that's that. All right, here we go. Let's say that we have f of x is equal to 2 secant x plus cosecant x all to the 8th. So this is stuff to the 8th, right? So I recommend just not even looking at what's on the inside here. It's just stuff to the 8th, right? That's what you're thinking of, stuff to the 8th. So the derivative will be, I bring the 8 down, I'll copy the stuff down, then I raise the stuff to the 7th. And now that I've done this, I will go ahead and put the stuff in. Just verbatim, you just copy it. Okay, just copy it. Then I'm going to put the derivative of the stuff in here. Okay, so the derivative of 2 secant x, well, that's going to be 2 secant x tangent x. And then the derivative of cosecant x is going to be negative cosecant x cotangent x. And that's that. I mean, I would leave this one like so. I mean, there's no reason to simplify this one any further. Okay. All right, let's take a look at another example. Let's say I have y is equal to e to the 2 plus 3x squared. Now this one you might think is a little tricky, but this is just e to the stuff. And what you're going to end up finding when you calculate this out is it's actually a chain rule within a chain rule. That can actually happen sometimes, right? So this is a chain rule within a chain rule. Okay, so now that we have all these rules, a lot of them can start mixing together. Okay. All right, but all I need to know is that the derivative of e to the stuff, that's the first thing I see. I just see e to the stuff, right? That's all I care about. And the derivative of e to the stuff is itself. So I just copy the whole thing down. Then it's going to be times the derivative of the inside. So here's the derivative of the inside. And when we go to take the derivative of the inside, this is going to be stuff squared. That's the case that we'll be dealing with. So when we do that, it's going to be, so now I'm looking at the derivative of 2 plus 3x all squared. So it will be 2 times the stuff left alone raised to the 1 and times the derivative of the inside. So now it's the derivative of that next inside piece, and that is going to be 3. Okay. And this one we can actually simplify quite a bit. We have this e to the stuff, and then we have this other thing. So we'll actually move that out front. So this will, 2 and the 3 come together to give me 6 times 2 plus 3x times e to the 2 plus 3x squared. And we are done. All right, next example, let's say we have the square root of x plus the square root of x. Okay, so first thing you'll probably want to do for this one is go ahead and rewrite it. Take that step to rewrite. So I'm going to have x plus x to the 1/2 on the inside, and that whole thing is raised to the 1/2. All right, and what this has done is it's changed this to this stuff raised to the 1/2 power. All right, so that's how I recommend trying to see what's going on here. Here's stuff to the 1/2 power. So the derivative with respect to x is going to be, well, I'll bring that 1/2 down, and it'll be 1/2 times that stuff to the 1/2 minus 1, so that would be negative 1/2. So I'll just copy the stuff down in there. Then it will be the derivative of the stuff on the inside, so, or of the inside. So the derivative of that stuff is going to be 1 plus 1/2 x to the negative 1/2. And there we go. There's another one I would leave just like that. I wouldn't bother simplifying that much further. Okay, next example here. F of x is equal to cotangent 3 times e to the sine of 2x. It's kind of difficult to see there probably. Sine of 2x. So this is going to be another chain rule within a chain rule, but no worries, right? All we're going to do is start with the fact that this is cotangent of stuff, right? So that's what we'll deal with. So for the derivative of cotangent of stuff, what's the derivative of cotangent? At this point you should be able to spit that out right now. What's the derivative of cotangent? That's right, negative cosecant squared. And I'm just going to copy this stuff down. So this will be negative cosecant squared, 3 e to the sine of 2x. Okay, so I just copy it down. And now here I'm going to put the derivative of the inside. So the derivative of the inside will have 3e to the stuff. So this is an e to the stuff case. So the derivative of e to the stuff is just itself. Times the derivative of the inside. So now, I'm put it in parentheses. Now I'm going to put the derivative of this inside stuff. So now I have the derivative of sine of stuff. So this is a sine of stuff case. So what's the derivative of sine? Well, we know, of course, that's cosine. So it will be cosine of the stuff. So the derivative of sine of stuff is cosine of the stuff. We'll just copy that down. Then times the derivative of the stuff, which is going to be 2. And I close off my parentheses, I close off my brackets. So if I wanted to write this, so this whole thing so it looked a lot cleaner, it'd be negative cosecant squared 3 e to the e to the sine of 2x. It's not as clean as I thought it would be. Okay. Times 3e to the sine of 2x times cosine of 2x times 2. So there it is, much cleaner. And some of this stuff can simplify a bit. Right, these constants I have can move on the outside, so I have negative 6, and the order you write the trig function and the exponential almost doesn't really matter, but let me move the exponential to the outside, e to the sine of 2x. Let me go ahead and move that cosine of 2 out as well, and then the whole thing is times cosecant squared of 3e to the sine of 2x, and there we go. Keep in mind, guys, that these are cosecant squared of. This isn't like a product. I see that mistake quite a lot, but here we go. That's our finished answer right there. Right, so that's actually a chain rule within a chain rule within a chain rule. But remember, you take it a step at a time, and you just keep taking derivatives of the inside until you're pretty much finished, right? Until you have no more steps to go, until you get down to something that's just in terms of x's, and then you can, well, finish up. Okay, here's another example for you. Say I have f of x is equal to 2 times 3 tangent squared x plus 1 raised to the negative 2. So all we really need to know at this point, this is stuff to the negative 2. Okay. What might help us in a second is this tan squared x. We can write that as 2, 3 times tangent x all squared. Okay, that might actually help us out, when it's all said and done. Okay, so f prime of x, remember this is still stuff to the negative 2, so it's going to be negative 2. I'm going to bring that negative 2 down, but since there's a 2 out front already, that will be negative 4 all times, okay, and I'll just copy the inside verbatim, raised to the negative 3. Then it's going to be the derivative of this stuff. And here, so we copy the stuff, we take the derivative of this stuff. Right? So now when I take the derivative of this stuff, well, that plus 1, that'll go to 0, so that's no problem. That constant 3 will come along for the ride. But now I have tangent of x all squared. This is stuff squared to the positive 2. All right, so I'm going to bring that 2 down and get 6 times tangent x raised to the 1. So it's just going to be 6 tangent x. And actually, let me go ahead and just raise that to the 1. Then times the derivative of the stuff, right? Because this is the stuff squared that we're dealing with. Right, so we're dealing with that inner quotient, or inner chain rule. So this was stuff squared, so it's 2, with the 2 down, raise it to the 1, and it's the derivative of the stuff, and the derivative of tangent is secant squared x. And that should be it, because we've exhausted all of our functions except for that plus 0 there. So we can close off that bracket. I always like to put the derivative of this stuff in brackets like that. And the only thing I would really do from here is maybe move this stuff around. I have this 6 and the negative 4, so this will come out to be 24. Tangent x, secant squared x, then all times 3. I'm sorry. Oh yeah, no, that's right. 3 tan squared x plus 1 on the inside. So I wrote it back again as tan squared x just to kind of keep the notation consistent. And there we go. So that is that example using the chain rule, right? So another chain rule within a chain rule. Again, don't get freaked out with those. Just Just take it a step at a time. Just think of what you have to start with, right? I didn't even think about what was on the inside, the fact that I had trig functions or anything. I just thought I had stuff to the -2. Then when I dealt with that piece, started worrying about the derivative of that stuff, I realized then I had some trig functions and another chain rule that I had to deal with. So with these, you're working outside in, essentially. Right, outside in. All right, the last type of example I want to look at is something that I should warn you, the course coordinator for this class loves this type of problem. It's a chain rule type problems that use a table that try to get you to deal with the chain rule in a more abstract sense. Okay, so for example, if I have that h of x is equal to f of g of x, right, and I'm told to find h prime of 1. So the first thing I want to do is find h prime of x. Now from the chain rule, h prime of x, that will be the derivative of this composition, f of g of x. Right? And by the chain rule, what that really is it's the derivative of the outside, right, f prime g of x times the derivative of the inside. Right? So this is by the chain rule. This is what the chain rule has been saying. And from here, if I wanted to find h prime of 1, well, I'd go to the table to find all my values, because I just plug 1 in for all my x's, so I'd get f prime of g of 1 times g prime of 1. So g of 1, so I go to my table where x is equal to 1, I go over to g, so g of 1 is 3. Right, so this is f prime of 3, I've just found here, then times g prime of 1, and g prime of 1, I didn't write this very well, but I go over to g prime in my table, and that's times 2. And I have one piece to finish off here. If I have f prime of 3, well, now I go to my x equals 3 column, go over across the row to f prime, which is -5. So I have -5 times 2, so the whole thing is equal to -10. Okay, so these actually end up just being a sense of finding the derivative abstractly, using what you know about the chain rule, and then it's just a matter of finding the pieces from the table. You know, they aren't my favorite type of question, but since, you know, you will see them quite a bit, well, maybe not quite a bit, but you'll definitely see them on the final, I can tell you that. They usually end up on the final. So you want to make sure that you're familiar with these types of questions. Let's say I had I is equal to, or I of x is equal to the square root of f of x, and I said find I prime of 2. Alright, so I prime of 2. Well, first we want to find I prime, and to do that, the best thing to start with is the fact that I'd want to simplify this, right? This would be f of x all raised to the 1/2. And then when I go to find the derivative, and that's what you always want to do first. If you're told to find I prime of 2, don't just take the derivative and try to plug in the value all at the same time. First of all, it's just tacky. I mean, it looks bad when you try and do that. Okay, and second, it's a great way to make a bunch of mistakes. Okay, so first, just find I prime of x. So I prime of x, well, I have stuff to the 1/2. So this will be 1/2 times that stuff, which is just f of x, raised to the -1/2, all times the derivative of the inside, and the derivative of the inside is just going to be f prime of x, right? Since I don't know what f is, the best I can do is just put times f prime of x. And from here, now we just go to the table, because I'm just going to plug 2 in for all my x's. I have 1/2, and this will be f of 2
raised to the negative 1/2. Let me erase that because it looks bad. Times f prime of 2. Okay, so this is going to end up being... Alright, and let's go to my table. I'm looking for f of 2 here. So f of 2. Go to my x equals 2 column. Go over to f. F of 2 is 3. So that'll be 1/2 times 3 to the negative 1/2. And then I need f prime of 2. So f prime of 2 is 2. Okay, and hey, that 1/2 and that 2, they cancel. Sorry about that. And so I basically get 3 to the negative 1/2. And if I wanted to simplify that, that's 1 over 3 to the 1/2, also known as 1 over the square root of 3. And we can just leave it like that if we like. Okay. And there you go. Let me do another with this table, just so you have another example of how it works. Let's say I have j of x is equal to e to the g of x all squared. Okay, and I want to find with the table j prime of 3. Right? So what I'm going to do is first find j prime of x. Always do that first. J prime of x. Now this is e to the stuff, right? So this is e to the stuff case. So its derivative will be itself. Okay? Then times the derivative of the stuff, and the derivative of the stuff, I did that wrong, d over dx of the stuff. The derivative of the stuff, well, that's actually and for some reason I wrote a 2 there. I don't know where that came from. The derivative of the stuff, this is stuff squared. All right, so this, you can think of the second stuff squared. So it will be 2 times g of x raised to the 1. Okay, so that's that, 2 times the stuff raised to the 1 times the derivative of the next stuff. So this will be the derivative with respect to x of the second stuff that we put here. And that's g. And the derivative of g is g prime. Okay, so let me simplify this out a bit. This is going to be 2 times g of x times g prime of x times e to the g of x squared. And now I'm going to put in the 3. Right, so j prime of 3 is going to be 2 times g of 3 times g prime of 3 times e to the g of 3 squared. And we find all these values from the table. So first I'm going to look for g of 3. G of 3, g of 3. G of 3 is thankfully 1. That's actually going to simplify things quite a lot. So g of 3 is 1, so I get 2 times 1 times something. I'll fill that in a second. All to the e raised to the 1 squared. Then for this piece I need g prime of 3, and g prime of 3 is actually 20. I go 3 over to g prime, that's 20. So I'll fill that in. And so I have basically 40 times e to the 1, which is just 40e. And we finished that off. So yeah, I know it's kind of obtuse, kind of yeah, weird little problem. But it does, I think, actually help see the chain rule in a different light, because here we're looking at the chain rule in a more general sense with G's and F's, and that's actually going to help us a lot in the next section, 3.7, which is all about implicit differentiation. And implicit differentiation, 3.7, is really all about
using the chain rule when you don't know what that inside function is, right? We'll be using y's mostly there instead of, say, f of x's, but that's really the whole thing about implicit differentiation is chain rule where you don't know what the inside function is, but you can still do it because all you've got to do is multiply by the derivative of the inside. Okay, so that's enough for now, I think, and I will talk to you then. All right, cheers.